one sample. So we took one sample and calculated a sample proportion, or we took one sample and we calculated a sample mean. What we're going to talk about in Chapter 10 is what happens when we actually take two separate samples that we need to analyze together. So to see if one was better than the other, or if one was different than the other, or something of that nature. Okay? So in Section 10.1, so it's going to have 3 different days worth of 10.1. We're going to talk about the sampling distribution. So what does the actual distribution look like when we compare differences between two proportions? Then we're going to get into what the confidence intervals look like tomorrow. And then we'll talk about how to run hypothesis tests. So we're going to do it kind of one step at a time for proportions. And then the second section of Chapter 10 is going to work with means. So what does the confidence intervals for the difference of means look like? What does the test look like for running the difference of means and things like that? Okay? So the whole purpose of this chapter is that in the real world, comparisons between two samples are often more interesting or more informative than looking at simply one single isolated percentage or one single isolated mean. So comparing between two separate groups a lot of times can give us more information, or it's more interesting than just looking at, well, how did this one group do? Okay? So we want to often know how two groups differ. For instance, in an experiment, we want to know if the treatment actually improved results, or is the placebo just as effective? So is our treatment actually effective as far as working with this, but whatever we're working with? Whether this year's results are better than last year's. So how do things compare? That's going to be kind of the goal here. Two separate samples, how do they compare to one another? So the ideal strategy, the way we're going to kind of attack this, is to take separate random samples from two separate populations and compare. So in this section, we're going to focus only on proportions. When we get into the next section, we'll talk about means. So we're going to take two separate samples from two separate populations. We're going to take the sample proportion of one, compare it to the sample proportion of the other. So that's kind of our goal in this particular unit. So some things to kind of keep note on these, some notation. Now this notation can change based on what you're working with within the problem. Sometimes the numbers make more sense. I'll show you how to do it if we need to use letters to denote certain aspects. Okay? But basically what's going to happen here is we're going to have two separate populations. So in this case, population 1 versus population 2. Now, if we know the true proportion from population 1, that would be p sub 1. If we know the true proportion from population 2, that would be p sub 2. So p is utilized for the parameter that came from the population. In most cases, we won't know that parameter. We won't know what the true proportion from our population looks like. So we would use the statistic instead. We would use p hat for population 1, or p hat sub 2 for proportion 2. So in most cases, this is what we're going to be working with, especially when we're working with confidence intervals. If we're doing a mean, or I'm sorry, if we do a test, we use the parameter value because we're assuming something about the population. And then the other thing to keep track of are your different sample sizes. Okay, so how big a sample did we take from group 1? How big a sample did we take from group 2? Now again, you can use the notation with the numbers. But in some cases, calling something 1 and calling something 2 might not be clear, and you can get lost in what you're actually doing if you don't continuously go back and look at, well, what did I say 1 was, or what did I say 2 was? So if, for instance, you were working with a problem or a scenario where one population of interest was all males and another was females. Okay, so population 1 was from males, population 2 is females. Well, instead of saying males are 1, females are 2, and then having to keep track of that as you work through the problem, you could do the same thing using letters as well as notation. So you could say, like for this one, this would be the true proportion for males, this would be the true proportion for females. Or this is the sample proportion for males, this is the sample portion for females. So you can use lettering to kind of help you denote the different populations as well. So you just need to make sure that when you write your notation, you know which proportion that particular value is pertaining to and which sample size that particular value is pertaining to. Okay? Now, can we put phones away, guys? If you're not following the notes online, let's get those away. So, to explore, to start with, so today we're not going to go into intervals, we're not going to go into hypothesis testing, we're just going to talk about the sampling distribution. What does it look like if we take two different samples and bring them together? Okay? So, if we want to explore the sampling distribution for the difference between two proportions, so whenever we compare two separate groups, we're going to compare based on differences. We've seen that idea before when we did the paired t-test last chapter. We had two different groups. We put the two groups together as one through the differences in the values. So this is the same idea. The only difference is this time we don't have paired data. They're not related. They're two completely separate groups of people, which means we have to treat them completely separately. We can't combine them into one set of data. Okay? So, we're going to start with two populations where we know a proportion of success. So at school 1, 70% of students did their homework last night. At school 2, 50% of students did their homework last night. So these are parameter values. They went to every single student and they checked. 70% of school 1 did their homework, 50% of students at school 2 did their homework. So we're starting off knowing that information. In a confidence interval problem, we wouldn't know this. Okay? But for right now, we're assuming we know, and then we're going to show what kind of happens when we look at the difference between these two schools. So, the way this would work then, we have population 1, which is coming from school 1, and we have population 2, coming from school 2. So at school 1, the counselor takes an SRS of 100 students, records the sample proportion of students who did their homework. So she just went out and selected a random sample of 100 students, figured out how many of them did their homework, calculated the proportion. School number 2's counselor takes an SRS of 200 students, records the sample proportion of students who did their homework. So this counselor number 2 calculated the proportion based on an SRS of 200 students. Now, if we were to do that process over and over and over again, so if counselor 1 took that first sample and recorded the proportion, and then went back out for another sample and recorded that proportion, and then went back out and so on, and counselor 2 did the same process, we do it over and over and over again. What ends up happening is we create a sampling distribution for the true proportion of students who did their homework the night before. So what you're looking at here is computer software output. So they actually ran the simulation. In school 1, they took samples of 100 over and over and over again, and they calculated the sample proportions and recorded that. So these dots are representing an individual sample proportion. So they went or used the exact same information. They did the process 1,000 times. So they took 1,000 different samples of size 100 from school 1. They did 1,000 different samples of size 200 from school 2. So these first two distributions that you're looking at, these are the sampling distributions for only the schools individually. So school 1 and school 2. Now if we take a look at the summary statistics, we should see exactly what we'd expect based on what we learned from chapter 7. So the center, well first of all the shape. We took an SRS of 100 over and over and over again. The shape appears to be approximately normal. That's expected. When we take large enough samples, we should get a normally distributed distribution. The mean, so the center, should happen at the true population value. We knew that 70% of students at school 1 did their homework. So the mean should be at 70%, which it is. as far as the spread, when we calculate standard deviation, that would be P times Q divided by N, all under the square root. Okay, so the standard deviation of this distribution would be the 0.7 times its complement 0.3 divided by 100, and then we take the square root of that. When we look at school 2, it's also approximately normal, which we would expect. The mean happens at 50%, again, like we would expect, and the standard deviation happens in the same regard. P times Q over N, all inside the square root. Now, this is what they look like separately. But we said we want to compare. So we want to know what happens if we take the difference between these two schools. So notice they took school 1 minus school 2. So they said out of these 1,000 and out of these 1,000. So when they took their first sample, they each calculated proportion for each sample, and then they subtracted them. And then they went to the next sample and subtracted, and the next sample and subtracted, and recorded those differences. And those recorded differences are represented by each of the dots within this distribution on the right here. Now notice, when we look at the shape, it's again approximately normal. If we take one normal distribution minus another, we should continue to stay normal. Okay? What do you notice about the center of our distribution? Where's the center located? Point 2, which is the exact difference between population 1 and population 2. We knew 70% of students in school 1 did their homework, 50% in school 2 did. So there's a 20% difference, right? And that shows up exactly like it should within our distribution here. So the mean of our distribution, when we take the difference of two proportions, should happen at that expected difference. Where that changes it would be in the standard deviation. So as far as mean goes, the center is going to be the center no matter what. So if we take the mean of one minus the mean of the other, we just get the new mean. Okay? So when we compare, now what's happening here, the way we are creating this new distribution is a lot like working with those random variables from last semester. So if I took one random variable minus another random variable, their means subtracted exactly like they should. Okay? Now, standard deviation was a little bit different. When we took one variable minus another, and we wanted to combine those, what did we actually have to do with the standard deviation? We didn't need to standardize. So when I took x minus y, the value was the difference of the means, right? So when we looked at the mean, the difference was exactly like it should be. But when we looked at standard deviation, we had to add the variance. So what happens here, notice, if I take the standard deviation of one and the standard deviation of the other, if I subtract these, I do not get my new standard deviation because standard deviations don't subtract. The other thing is, if I tried to add them, if I take this standard deviation plus this standard deviation, it does not equal the standard deviation for my difference. The standard deviations don't add either. What does add is variance, the standard deviation squared. So, if I were to take PQ over N from population 1 plus PQ over N from population 2, so if I took those variances and add them together, then when I take the square root, I get my resulting standard deviation. So the fact that they had different sample sizes didn't change the fact that the mean subtracts just like it should. But what it changes is how that standard deviation combines. So we take it into account at that point. So basically what we're saying here is when we do a sampling distribution for the difference of proportions, it's going to be treated pretty much identically to any of the sampling distributions we worked with in Chapter 7. So the mean still happens at the true population value. The standard deviation, though, is a combination of variances. So when you describe a sampling distribution for the difference of proportions, so when we have two separate sample proportions and we want to describe the distribution, we need to look at three aspects. What would the shape look like? What would the center be? And what would the spread be? So, in these instances, we have two different populations. So we're going to choose an SRS of size N1. We're going to calculate P1 from that sample. We need an independent SRS of size N2 from population 2 with a known proportion from that sample. Okay? So we have two separate populations. Now, a lot of the stuff here should look pretty similar to things we've been dealing with the past couple chapters. Note that when I want to describe shape, it's going to be approximately normal if NP and NQ are both at least 10. The difference here is now we have two separate populations to account for. So when I check NP and NQ, I need to do NP and NQ for population 1, and I need to do NP and NQ for population 2. So when you check this first part, when you talk about shape, you need to check that large counts condition. So sample 1 times the population proportion, and then sample 1 times the complement. If those are both at least 10, then you can check your second population. So take N2 times P2, and take N2 times Q2. And those have to be at least 10 as well. So it's the same condition that we checked before, it's just now we have to do it for both populations. Get it? All right, so if that works, we get a normal distribution. Now for the center, if we want the center of our sampling distribution, so the mean, if I'm going to take the mean of two sample proportions, it should line up exactly with the population proportions. So if I take P1 minus P2, that's going to give me the exact center of my new distribution. And then the spread, when we want to calculate the standard deviation, the standard deviations individually do not add together. So it's not the square root of PQ over N plus the square root of PQ over N. That doesn't work. We need the variances to add, and then we can take the square root for standard deviation. So here, the only difference is we take PQ over N plus PQ over N, then we do the square root. So in a problem when you do that with your calculator, you want to be very careful with how you work that out. So do your PQ over N plus PQ over N, and then take that square root to get your actual value. Now, when you do the spread, in order to calculate the standard deviation using this formula, you need to check your 10% condition. And again, since we have two separate populations of interest, we need to check that the sample for population 1 is less than 10% of population 1, and we need to make sure that the sample for population 2 is less than the population, or 10% of the population. So everything about this is identical to what we've done before. The only difference is when we check our conditions, we have to account for both populations. Everything else should be the same. So when you go for shape, check your large counts condition. If it works, your value or your distribution will be approximately normal. For the center, just take the two known proportions and subtract them. And for standard deviation, check your 10% condition, and then PQ over N plus PQ over N, take the square root. Okay? So let's run through an example. So your teacher brings 2 bags of colored goldfish crackers to class. Bag 1 has 25% red crackers, and bag 2 has 35% red crackers. Each bag contains more than 1,000 crackers. Using a paper cup, your teacher takes an SRS of 50 crackers from bag 1 and a separate SRS of 40 crackers from bag 2. We're going to let P hat 1 minus P hat 2 be the difference in the sample proportion of red crackers. So basically what we're asking here is if we were to do this over and over and over again. So if we were to take that paper cup and take an SRS of 50 from bag 1, take an SRS of 40 from bag 2, and then we did that process over and over again, what would our distribution look like? So when we actually do the difference between the two proportions that we calculate, what is the overall distribution going to look like? So, what would the shape of my distribution look like and why? So if I want to find the shape of my distribution, what condition do I need to check? The large counts. So I need to take N1 times P1. So what is N1? So we take an SRS of 50 from bag 1. So N1 is 50. What is P1? 25%. Bag 1, we know, has 25% overall. So in your calculators, take 50 times 0.25. What do you get? $12.5. Is 12.5 larger than 10, or at least 10? Yes, so then let's go to N1 Q1. So N1 is still 50, Q1 would be 75%, so 50 times 0.75 would be 37.5, that's at least 10. Now we need to check our second population, so bag 2. So from bag 2, we took a sample of 40. So if I take 40 times P2, so 40 times 0.35, what do we get? 14, that's at least 10. So now we can check NQ. So 40 times 0.65, 326. Okay? So because all of our NPs and NQs were at least 10, what should our shape be? Approximately normal. Okay? So your first step when you're looking at shape is check your large counts, NP1 and NQ1. Are they at least 10? If so, proceed to the next, NP2, or into P2 and into Q2. And if all of them are at least 10, then your distribution will be approximately normal. Okay? If at any point you run into one that's not at least 10, you can stop immediately and say the large counts condition is not met, which means we don't have a normal distribution necessarily. Okay? So when they ask you to describe the shape, this is your process. Check NP and NQ for both. If it works out, then you have an approximately normal distribution. We okay with that? Okay? Not for proportions. So when we get to means, with means we have that n has to be at least 30. So that would be one we can do that. But for here we have to check NP and NQ. All right, next question. What would be the mean of our sampling distribution? So if we took P hat 1 minus P hat 2, we did it over and over and over again. Where should the center of the distribution lie? At the actual difference. And what would be the difference? If we're doing P1 minus P2, the mean would be at 25 minus 35, which would be negative 10%. So the means of our distributions can be in the negatives. What that means is we can expect 10% less in bag 1 than we can in bag 2. And this is going to be one of those types of problems where you can set up your difference in different manners. Whether you like positive or don't care and work with negative, you can do it either way. So in our case, since we established 1 minus 2, we have to do everything in that order. So that's why we're going to get a negative mean. If we wanted to flip the order, we'd get a positive mean, then we'd just be changing some of our calculations a little bit. Okay? So the mean of our distribution is the difference between population 1 and population 2. Then the last part is calculating standard deviation. So if I want to find the standard deviation for the sampling distribution, what condition do I have to check first? 10%. So sample 1 was 50. Is 50 less than 10% of 1,000? Yeah, if I take 50 times 10, that'd be 500 crackers. 1,000 is above that, so we're less than 1,000, or less than 10%. Or we could actually do 50 divided by 1,000. It's going to be less than 10%. And then we have 40, which is definitely going to be less than 10% of 1,000. Okay? So, when that's true, how do I calculate the standard deviation for the difference here? Take the variances. So do PQ over N for 1 plus P2 or PQ over N for 2. So the process here, our 10% condition is met because both samples are less than 10% of the population. So when I go to calculate my standard deviation now, I take PQ over N for sample 1 plus PQ over N for sample 2. So 25% times 75% over 50, and then 35% times 65% over 40. So I add those two values together and then take the square root of that result. And so we end up with a standard deviation of 0.0971.
That's always add, right? You always add.
Mm-hmm. Always add them, no matter what. So PQ over N plus PQ over N, square root. Good there? So shape, check what? Large counts. If it works, then, well, if it works, then the shape is, approximately normal. Then we would check center. Center is just the difference, so just subtract the two values. And the standard deviation, we check 10%, and if it works, then PQ over N plus PQ over N, square root. Okay, that's it. 2 problems.